If you could escape the pull of Earth and rise above the stars, you'd see our galaxy, the Milky Way, stretched out like a glowing pinwheel in space. It looks calm, but that illusion hides a galaxy in motion. Inside it, stars are being born and dying. Entire star systems are whipping around at incredible speed. Giant clouds of gas are drifting, collapsing, igniting. And at its heart lies a beast of epic proportions. Only recently have we started to understand what the Milky Way really is like. We've mapped its spiral arms and discovered its satellite galaxies, but there's still so much we don't know. In this journey, we'll follow these threads and piece together one of the most epic stories in the universe, the story of our galactic home. Before the Milky Way had a name, ancient eyes gazed upon the galactic river. Long before science gave it a name, long before humanity even understood what stars truly were, there was a band of pale light stretched across the night sky. People everywhere could see it when the nights were clear. It arched overhead like a great path in the heavens. Some saw it as smoke, others thought it was a river. Many believed it was the trail left by gods or spirits. This was the Milky Way, though no one called it that yet. In those ancient times, people did not think of space the way we do now. They had no tools to measure light or distance. They had no way of knowing that this pale band was made of countless stars. All they had were their eyes, their stories, and their skies. The ancient Greeks, who were among the first to give written names to the stars, saw the Milky Way as a product of myth. One of the most popular legends comes from the tale of the goddess Hera and the infant Heracles. As the story goes, Heracles, born of a mortal woman but fathered by Zeus, was brought to Hera to nurse while she slept. When Hera woke and realized the trick, she pulled away, and her divine milk spilled across the sky, forming the Milky Way. The Greeks called it Galaxius Kyklo, the Milky Circle. This is the origin of the word galaxy. In ancient China, astronomers kept detailed records of the stars for centuries. They had their own name for the Milky Way, the Silver River. To them, the band of light was a celestial waterway. One of their most beloved stories tied to it is the legend of the Weaver Girl and the cowherd. According to this tale, the two lovers were separated by the Silver River, allowed to meet only once a year, when a bridge of magpies formed across the sky. Today, this story is still remembered in the Qixi festival, sometimes called Chinese Valentine's Day. The stars representing the lovers, Vega and Altair, still shine across the Milky Way, their positions in the sky changing with the seasons. Further west, in what is now the Middle East, ancient Mesopotamians had their own interpretations. In Babylonian culture, the sky was deeply tied to gods and fate. The Milky Way was thought to be the tail of the great sky dragon Tiamat, or sometimes a river used by the gods. Babylonians believed the heavens mirrored the earth, so it made sense that a shining path across the sky might be the reflection of a river below, perhaps their own Tigris or Euphrates carried into the stars. In Africa, traditions varied by region. Among the San people of southern Africa, the Milky Way was seen as the spine of the night. Some stories described it as the dust of travelers kicked up by people walking along the path to the afterlife. It guided souls to where they needed to go. In parts of West Africa, it was known as the backbone of night, a phrase that would later be used as the title for a modern documentary on astronomy. In Northern Europe, the Norse had stories of their own. The Milky Way may have been seen as a road used by the gods, perhaps the Bifrost Bridge that linked Earth to Asgard. While the Norse myths are better known for their tales of Thor, Odin, and the end of the world, they also describe a sky full of meaning, where every star had a role in the fate of men and gods alike. Among the indigenous peoples of the Americas, the interpretations were often poetic and rooted in the rhythms of nature. The Inca saw the Milky Way not just as a band of stars, but as a place filled with dark shapes, what we now call dark nebulae. These were not empty spaces, but celestial animals, a llama, a fox, a serpent. To the Inca, these forms were real and vital. They watched the dark shapes shift through the seasons, using them as signs for planting, harvest, and ceremony. The Lakota people viewed the Milky Way as the spirit path, a road taken by souls after death. Other Native American groups, such as the Cherokee, had stories that saw the Milky Way as cornmeal scattered by a dog running across the sky. Even in regions where writing had not yet developed, oral traditions kept these ideas alive. The Aboriginal Australians, with some of the world's oldest continuing cultures, had remarkably detailed sky stories. The Yolngu people saw the Milky Way as a canoe carrying ancestral beings. Its shimmering light was the reflection of their fires on the surface of the water. These stories were maps, calendars, and moral lessons, all wrapped in the stars. Without telescopes or science, people still knew the Milky Way mattered. They gave it stories and names because it touched something deep inside. Of course, none of these ancient people knew that what they were seeing was the edge-on view of our spiral galaxy. They didn't know that the stars they saw were only a small part of a vast system containing billions of suns. But what they did know, what they could feel, was awe, and from that awe, they built the foundations of wonder, curiosity, and eventually science. When the stars began to move, the disruption of the geocentric universe, for a long time, people believed the Earth was still steady, and at the center of everything, the sky, they thought, moved around them. The sun rose and set. The stars circled overhead. The moon traveled across the heavens. This made sense to the human eye. After all, the ground didn't seem to move. The stars, planets, and the sun appeared to dance around us. It felt right to believe that Earth was the center of the universe. This idea was supported by the most influential thinkers of the ancient world. The Greek philosopher Aristotle believed that the heavens were perfect and unchanging, with Earth fixed in place at the center. Later, the astronomer Ptolemy built a detailed model of this geocentric system. In it, the Earth sat still while the planets, sun, moon, and stars spun around it in perfect circles. Ptolemy's system was complicated. It required planets to move in small circles as they orbited in larger ones, known as epicycles. But it seemed to match what people saw in the sky. For over 1,000 years, this model was taught as fact. It shaped the way people thought about the universe, about their place in it, and even about how time works. The Church in Europe accepted this model too, since it matched certain religious views that placed Earth and humanity at the center of God's creation. Questioning the structure of the heavens was not only seen as foolish, it was dangerous. But then something began to shift. In the 1500s, a quiet but radical idea started to take form. A Polish mathematician and astronomer named Nicolaus Copernicus began to wonder whether Ptolemy's model really made sense. The motions of the planets were too messy under the old system. Some wandered backwards in the sky, something called retrograde motion, and the circles within circles that Ptolemy used to explain this felt forced. What if, Copernicus thought, the problem wasn't with the planets, but with us? He proposed a new model. What if the sun, not the Earth, was at the center of the universe? What if the Earth spun on its axis and moved around the sun once a year? This idea, the heliocentric model, made the backward movement of the planets much easier to understand. It was a simple and elegant idea, but it was also deeply unsettling. Copernicus hesitated to publish his work. He knew it would be controversial. He spent decades perfecting his book, On the Revolutions of the Celestial Spheres, and only allowed it to be published shortly before his death in 15. By that time, his health was failing, and he may have never known how much trouble and inspiration his idea would bring. At first, not much changed. Copernicus's book spread quietly, read mostly by other astronomers. Many still clung to the old geocentric system, but among those who read it, something had started to crack. The idea that Earth wasn't the center, that we were just one planet among others orbiting the sun, was slowly taking root. Then came Galileo Galilei. Galileo was born in Italy in 1564. He was curious about the world from a young age. He studied motion, built machines, and tested ideas that others had only talked about. But one invention changed everything for him: the telescope. The telescope had just been invented in the early 1600s. and it didn't take long for Galileo to improve on its design. When he pointed it toward the sky, he saw things no human had ever seen in such detail. He saw craters on the moon. He saw sunspots on the sun. He discovered that Jupiter had moons, 4 of them, that orbited the giant planet. And he saw that Venus went through phases just like our moon, something that could only be explained if Venus was orbiting the sun. All of these discoveries pointed in one direction. Earth was not at the center, the heavens were not perfect, and the old models could not explain what Galileo was seeing through his lens. He published his findings in 1610 in a short book called Starry Messenger. It caused an uproar. The church, still deeply tied to the Ptolemaic view, reacted with alarm. Galileo's ideas were seen as a threat to religious authority. In 1616, Copernicus's heliocentric theory was officially labeled heretical. Galileo was warned not to teach or support it, but Galileo did not stop. He continued to write, and in 1632 he published Dialogue concerning the two chief world systems. Though it was written as a conversation between 3 characters, the book clearly supported the sun-centered model. The response was swift. Galileo was brought before the Roman Inquisition. He was forced to recant his views and spent the rest of his life under house arrest. But the damage to the old model was done. The telescope had revealed too much. The stars were no longer just distant lights on a black dome. They were something more, perhaps suns in their own right, each far away in a vast darkness. As the years passed, more astronomers built on what Copernicus and Galileo had begun. Johannes Kepler discovered that planets moved in ellipses, not perfect circles. This made the motions of the planets match observations with far greater accuracy. He also found that planets moved faster when they were closer to the sun and slower when they were farther away, a discovery that added power to the heliocentric model. Then came Isaac Newton. In the late 1600s, Newton explained why the planets moved the way they did. He described gravity, a force pulling objects together, and showed that the same force that made an apple fall from a tree also kept the moon in orbit. With Newton's laws, the motion of the planets could be predicted. The solar system became a machine that followed rules. But while this explained the motions of planets and moons, it also raised a new question. If the Earth was not the center, and the sun was just one star, what were all those other stars in the sky? Through the 1700s and 1800s, telescopes improved. Astronomers began to see that the sky was filled with stars too faint for the naked eye. Some clusters looked cloudy. These were called nebulae. Some of these, it would turn out, were not clouds at all, but vast collections of stars far beyond our own solar system. Slowly, the idea of the universe began to stretch. The Earth moved around the sun. The sun was just one of many stars. The stars might be part of a larger system too, a system we would one day call the Milky Way galaxy. For thousands of years, people had looked up and believed that all of it moved around them. That belief shaped entire civilizations. But through patient study, new tools, and the courage to question what had always been accepted, the old universe began to fall away. In its place, a larger, more complex, and more awe-inspiring universe was being revealed, one in which Earth was not the center, but part of something much greater, still waiting to be understood. Even when telescopes showed that the Milky Way's glow came from stars, millions and millions of them, a bigger question remained: what was the shape of it all? What was the true form of the galaxy we lived in? That turned out to be a very hard question to answer. The biggest problem was our location. We are inside the Milky Way, buried deep within one of its arms. It's like trying to figure out the shape of a forest while standing among the trees. You can see trunks and branches around you, but the full pattern, the whole forest, is hidden. There was another problem too. Between the stars are thick clouds of gas and dust. These clouds block visible light. So even if a distant part of the galaxy was out there shining brightly, much of that light never made it to Earth. It was hidden behind the dark curtains of the Milky Way's dusty lanes. For years this made progress slow. Early astronomers counted stars and tried to map the sky, hoping to figure out where the galaxy was thickest or brightest. In the late 1700s, astronomer William Herschel attempted just that. He made rough star maps and proposed that the galaxy might be shaped like a flattened disk, but without a way to see through the dust. His map was more of a guess than a true picture. Everything changed when scientists learned to look beyond visible light. Light comes in many forms, not just the kind our eyes can detect. There are wavelengths that are shorter, like ultraviolet and X-rays, and ones that are longer, like infrared and radio waves. These longer wavelengths have a special ability. They can pass through dust. Infrared light is close to visible light, just beyond the red end of the spectrum. It comes from warm objects like stars hidden behind thick clouds. Radio waves are even longer. They can travel through thick clouds of gas and dust almost without being disturbed at all. These invisible signals held the key to uncovering the Milky Way's true shape. In the mid-20th century, a new kind of astronomy was born: radio astronomy. It didn't use glass lenses or mirrors. Instead, it used giant metal dishes to collect faint radio signals coming from space. One of the first big discoveries came from looking at the hydrogen atom. Hydrogen is the most common element in the universe. In deep space, most of the gas between stars is made of it. When hydrogen atoms flip their internal spin, they release a radio wave with a very specific wavelength, 21 centimeters long. This signal, though incredibly faint, can be picked up by radio telescopes. In the 1950s, astronomers started using this hydrogen signal to map the Milky Way. As they listened to the radio waves coming from different directions, they noticed that the hydrogen wasn't spread out evenly. It was gathered in long, curved paths, structures that wrapped around the center of the galaxy. These were spiral arms. It was one of the first clear signs that the Milky Way was a spiral galaxy. Instead of a smooth, round cloud of stars, it had a structure, arms that curled outward from a dense central region. Infrared telescopes were the next big step. In the 1980s and 1990s, NASA launched missions like the Infrared Astronomical Satellite, IRAS, and later the Spitzer Space Telescope. These observatories orbited above Earth's atmosphere, which blocks much of the infrared light from space. Up there, free from atmospheric interference, they could see the heat glow of stars and gas that visible light telescopes could not. With these tools, astronomers were able to peer into the dusty core of the Milky Way for the first time. What they found was a crowded, complex region full of stars and strange structures. At the heart of it all was a bar-shaped cluster of stars stretching through the center. This meant that our galaxy was not just a simple spiral, but a barred spiral, a form seen in many other galaxies across the universe. Infrared and radio maps started to overlap. The data was combined to show the Milky Way in new ways: a thin disk with curved arms, a thick bulge in the middle, and a surrounding halo made of older stars and mysterious dark matter. It was a galaxy much like others, but to us, it was home. Still, even with this new understanding, mapping the Milky Way remained difficult. Unlike distant galaxies that we can see as whole objects in the sky, we can't look at our galaxy from the outside. Every map of the Milky Way is a reconstruction, pieced together from signals coming in from all directions. To make these maps, astronomers use another tool: Doppler shifts. Just like the sound of a passing train changes pitch as it moves, light and radio waves also shift depending on whether the source is moving toward or away from us. By measuring the shift in the 21 centimeter hydrogen line, scientists can figure out how gas clouds in the galaxy are moving. These movements help reveal where the spiral arms are and how they rotate. All of this work has painted a clearer picture of the Milky Way. We now believe it has 4 main spiral arms, though some are more well-defined than others. Our solar system sits in a smaller branch between 2 of them, known as the Orion Arm or Orion Spur. From inside, the Milky Way still looks like a streak of stars and dust, but thanks to the patient work of many scientists and engineers, we've pulled back the curtain, and we now know that we live in a majestic spinning city of stars, with curved arms stretching across hundreds of thousands of light years. Even now, the picture is not complete. Parts of the galaxy remain unmapped, hidden behind thicker clouds or confused by overlapping signals. But every year, new instruments and missions continue the work. Space-based observatories, ground-based radio arrays, and detailed computer models are helping to sharpen the view. What once seemed like a hazy trail of stars has become a vast spiral system. The Milky Way is still revealing itself piece by piece, and with each new discovery, we are reminded of how far we've come from the days when people thought the stars circled the Earth. Now we know we are the ones who move, spinning quietly inside a galaxy full of wonders. Finding our address in the cosmos, the solar system's place in a rotating giant. From Earth, the sky looks the same in every direction. The galaxy doesn't come with a map, so scientists had to make one. Back in the 1700s and 1800s, astronomers like William and Caroline Herschel tried to count stars in different parts of the sky. The goal was simple: see if there were more stars in one direction than another. The assumption was that if we were near the center of the galaxy, we'd see a roughly even number of stars in all directions. If we were off to one side, then one part of the sky should be more crowded. Their early maps were a good first try, but they were limited. Still, it was enough to suggest that we weren't in the center of the Milky Way. The star count seemed to cluster more heavily in certain areas, hinting that we weren't anywhere near the middle of it. Later, as telescopes improved and photography came into use, astronomers started looking at special types of stars to help measure distances. One of the most useful was the Cepheid variable star. These stars grow brighter and dimmer in a regular rhythm, and their brightness is tied to how long that rhythm lasts. By measuring the time between their pulses, astronomers could figure out how bright the star really was, and then by comparing that to how bright it looked from Earth, they could calculate how far away it must be. In the early 20th century, this method helped unlock the scale of the Milky Way. It showed that the galaxy stretched far beyond what most had believed. And again, it confirmed that the Sun was not at the center. In fact, we were quite a distance away, tens of thousands of light-years from the dense hub of stars and gas in the galactic core. Later studies using more Cepheid variables and other types of stars showed that the solar system sits about 26,000 light-years from the center of the Milky Way. That's roughly halfway out from the center to the outer edge of the disk, which stretches to about 100,000 light-years across. But knowing our distance from the center was only part of the puzzle. Scientists also wanted to know what part of the galaxy we were in. The Milky Way, after all, has arms. Spiral arms filled with stars, gas, dust, and new star formation. These arms wind outward from the center, wrapping around the galaxy like the arms of a pinwheel. Our solar system doesn't sit right on one of the big main arms. Instead, it lies in the Orion arm, a short, narrow bridge of stars that runs between two of the larger spiral arms, the Sagittarius arm and the Perseus arm. It's not a major highway of star formation, but it's still home to millions of stars, including our Sun. The Milky Way is not still. It spins. Everything inside it, including our solar system, moves. Stars orbit the galactic center the way planets orbit the Sun, though on a much grander scale. Our Sun, along with the planets that follow it, makes a full loop around the galaxy about once every 230 million years. This movement is called the galactic orbit, and our speed is about 8,200 to 8,000 kilometers, or roughly 514,000 blemos per hour. That motion is so smooth and constant that we can't feel it, but by measuring the light from stars and how it shifts, we can detect how fast things are moving. This is done using the Doppler effect. By looking at the motion of stars and gas clouds in different parts of the Milky Way, scientists saw that the galaxy rotated in a very particular way. The speed of rotation didn't drop off the way it should have if only visible matter were involved. This led to the idea that dark matter must be helping hold the galaxy together. But in addition to that major discovery, the rotation models also helped pin down our exact position. They showed how our solar system moves along its galactic path, and how it fits into the larger structure of the spiral arms. Another tool in finding our place in the galaxy came from pulsars. These are the collapsed remnants of massive stars that exploded as supernovae. Pulsars spin rapidly and emit radio pulses with extreme precision, almost like cosmic clocks, because each pulsar has a unique pattern. They can be used to measure distances and map locations with great accuracy. Some have compared this to the way GPS works here on Earth. By timing signals from several pulsars, scientists can triangulate positions and check galactic models. As more pulsars were discovered across the Milky Way, they helped confirm the structure of the arms and the motion of objects within them. They added to the growing map that showed where we live, not just our star, but its neighborhood within the spinning disk of the galaxy. Other nearby stars have also helped guide our understanding. For example, stars that are part of the same moving group as the Sun, the so-called local standard of rest, give us clues about how our area of the galaxy behaves. By comparing their speeds and directions, we get a sense of how the solar system fits into the larger traffic flow of stars orbiting the center. Today, thanks to all this work, we can point to a location on a map of the Milky Way and say, there we are, not at the center, but tucked partway out in a quiet arm between giants. We orbit with hundreds of billions of other stars, all of them moving through a galaxy that is both familiar and still full of mysteries. Measuring mass in a dark universe. When scientists try to measure how big the Milky Way is, they don't just look at how wide it appears. Instead, they look at how much stuff it contains, how far out its gravitational pull reaches, and how fast things are moving inside it. All of that helps build a more complete picture of the galaxy's true size and shape. But it also brings up a major problem. Most of the Milky Way's mass isn't visible, which makes measuring the galaxy a lot more complicated than it seems at first. The stars, gas, and dust we can see make up just a small portion of the Milky Way's total mass. These visible components form the bright spiral arms, the glowing core, and the scattered star clusters around the edges. If you added up all the light-emitting objects in the galaxy, every star, every planet, every glowing gas cloud, they'd only make up about 10 to 15% of the Milky Way's total mass. The first clues came from watching how stars move. In the early 20th century, astronomers began noticing that stars far from the center of the galaxy were moving much faster than expected. According to the laws of gravity, the farther you get from a central mass, the slower you should move, just like planets in our solar system. Mercury, which is close to the Sun, whips around it quickly. Pluto, far out on the edge, moves much more slowly. That's what physics predicts. But when astronomers tracked stars near the edges of the Milky Way, they weren't slowing down, they were moving almost as fast as stars closer to the center. That didn't make sense unless something invisible was keeping them moving. Something with mass, something that added extra gravity, holding the stars in place and speeding up their orbits. That something was called dark matter. Dark matter is the best explanation we have for a long list of strange observations. Not just in our galaxy, but in many others too. It doesn't interact with light, so it can't be seen directly, but it does interact with gravity. That's how we know it's there. And in the Milky Way, it seems to form a vast halo that stretches far beyond the visible edge of the galaxy's disk. This dark matter halo might reach out more than 300,000 light-years from the center, wrapping around the galaxy like an invisible shell. This changes how we think about the size of the Milky Way. If we only count the part that glows, we get the classic number, about 100,000 light-years across. But if we include the dark matter halo, the galaxy is much larger. Its true gravitational size could be 3 times that or more. It depends on where you draw the line, how far out the Milky Way's gravity still holds onto objects and satellites. The Milky Way has many smaller satellite galaxies orbiting it. Tiny systems of stars that cling to the galaxy's outer edges. The most famous are the large and small Magellanic Clouds. But there are many more, including some that are barely more than smudges of stars. These dwarf galaxies stay in orbit because of the Milky Way's gravitational pull. If the galaxy had less mass, they would drift away. The fact that they stay so tightly bound is one more clue that there's a huge invisible mass holding them in place. Measuring that mass is a pretty difficult task. You can't put the Milky Way on a scale. Instead, scientists use motion to estimate mass. The speed at which stars orbit the galaxy tells us how much gravity is acting on them. Faster speeds mean more mass. By mapping the rotation of stars at different distances from the center, astronomers can build a model of how mass is distributed throughout the galaxy. These models include both visible and dark matter, but the Milky Way isn't a simple flat object with evenly spaced stars. It has clumps, gaps, arms, and clouds. It has a central bulge of older stars with a halo that isn't perfectly round, and the dark matter doesn't clump the same way normal matter does. It spreads out more evenly, forming a smooth background structure that holds everything together. Every estimate, every model is built with gaps that have to be filled using math, theory, and comparison with other galaxies. Despite these challenges, astronomers have come up with a rough estimate of the Milky Way's total mass. Current models suggest it holds about 1 to 1.5 trillion times the mass of our Sun, but only about 100 to 200 billion of those suns are real stars. The rest of the mass, roughly 85 to 90%, is dark matter. That's an enormous amount of hidden material shaping everything we see and do within the galaxy. This dark foundation also affects how the galaxy interacts with its neighbors. The Milky Way and the Andromeda Galaxy are the two largest members of a group of galaxies known as the Local Group, and they're on a collision course. In about 4 billion years, the two galaxies will begin to merge. The outcome of that collision, how fast it happens, how violent it is, and what kind of galaxy emerges afterward, depends heavily on how much dark matter each one contains. Even now, the dark matter halos of the Milky Way and Andromeda may already be brushing against each other. That's how large and far-reaching they are. Long before the visible parts of the galaxies meet, their invisible components could already be influencing each other's motions. Not just a flat disk. The bulge, warp, and vertical flares of the Milky Way. If you imagine the Milky Way from the side, you might picture a flat spiral like a cosmic pancake. For many years, that was how people thought of it. But as we've looked closer through radio maps, space telescopes, and star surveys, that simple shape has started to come apart. The Milky Way bulges. Its edges rise and fall like ripples in a pond. And these odd shapes tell a deeper story about how our galaxy was born, how it lives, and how it may someday die. The most obvious bump in the Milky Way is the central bulge. From our position out in one of the spiral arms, we can't see the bulge with visible light because of all the dust in the way, but using infrared and radio waves, scientists have peered through the haze. What they found wasn't a perfect sphere or a simple ball of stars. Instead, the bulge is stretched. It forms a kind of bar, a long structure that cuts through the middle of the galaxy like a cosmic backbone. This bar shape is common in spiral galaxies. It's thought to form from the rotation of the inner disk, where stars and gas move in such a way that they begin to bunch up and stretch out. Gravity pulls on them, and over time the center of the galaxy becomes not just thicker but elongated. That bar then pushes gas inward, fueling new stars and feeding the black hole at the core. It becomes a kind of engine, driving changes in the center and setting off bursts of activity. Surrounding the bar is a dense population of old red stars. These stars are ancient, some of the oldest in the galaxy. Their presence tells us that the bulge formed early in the galaxy's life, but they're not the only things there. Hidden within the bulge are mysterious clouds of gas, regions where new stars are still being born. It's a place where the past and future of the Milky Way meet. Move away from the center, and the disk of the galaxy starts to do something strange. It bends. The outer parts of the Milky Way are warped, like a record that's been left in the sun too long. One side of the disk curves upward, while the other side dips down. This warp affects the positions and motions of stars and gas far from the center. Astronomers have measured this warp using surveys of hydrogen gas. They've also mapped the positions of stars and noticed the same bending pattern. It's not symmetrical, and it's not smooth. Some parts of the disk bend more than others. Some flare outward, like the edge of a wave just before it breaks. So what causes this? One idea is that the Milky Way's warp is the result of past encounters. Our galaxy hasn't lived a quiet life. It's surrounded by smaller galaxies, many of which have collided with or passed close to the Milky Way. These interactions can pull on the outer parts of the disk, like a hand tugging on the edge of a blanket. Over time, gravity from these passing companions can twist the galaxy's shape, leaving behind warps and waves. One of the most likely suspects is the Large Magellanic Cloud. It's massive enough to cause a ripple, and some scientists believe it could be shaking the galaxy even now. As it swings around us, its gravity may be pulling on the disk, creating a wobble that ripples outward. Another possible reason is the dark matter halo that surrounds the Milky Way. If the halo isn't perfectly even, if it's lopsided or offset, it could tug on the disk in certain places, causing it to bend and twist. As we move even farther out, the disk doesn't just warp, it flares. That means the farther you go from the center, the thicker the disk becomes. The stars at the edge don't sit in a neat flat plane. They rise and fall, forming a kind of bowl-like edge around the galaxy. This flaring is most obvious in older stars and in the outermost gas clouds. This pattern isn't fully understood, but it seems to be tied to how the galaxy grew over time. The outer regions are more fragile. They're more easily disturbed by passing galaxies or clumps of dark matter. These interactions can heat up the stars and gas, lifting them out of the disk and spreading them vertically. The result is a disk that gets puffier as you move outward, not because it was born that way, but because it's been pushed and pulled throughout its life. There's also the vertical structure of the Milky Way's disk. Not all stars follow a perfectly flat path. Some bounce above and below the plane, moving in wave-like motions. These ripples may come from past mergers, when the Milky Way swallowed smaller galaxies and the shock waves moved through the disk like tremors. Scientists have seen hints of this in the motions of stars recorded by the Gaia satellite. The stars don't just orbit. They pulse and shift up and down in ways that reflect a past full of collisions. All of these features show that the Milky Way is not a quiet, settled structure. It's alive with motion. Its shape is not frozen in time. The Milky Way continues to absorb smaller galaxies. The Large Magellanic Cloud is already affecting the Milky Way's halo, stirring up the dark matter and leaving ripples in the outer structure. In the far future, even larger events may reshape the halo once again, especially when the Milky Way collides with Andromeda. When that happens, the halo will become a storm of stars, streams, and shattered galaxies, all mixing together into something new. But until then, the stars of the halo remain where they are, moving slowly, quietly, in long paths around the galaxy. The tidal struggles of the Magellanic Clouds, out beyond the familiar arms of the Milky Way, are two bright spots in the night sky. They look like faint smudges to the naked eye, especially from the southern hemisphere, but they are full galaxies, the Large Magellanic Cloud and the Small Magellanic Cloud. These two dwarf galaxies are the Milky Way's closest companions, and for millions of years, they've been caught in a slow, twisting dance with our own galaxy. The Large Magellanic Cloud, or LMC, is the bigger of the two. It's about 160,000 light-years away, close in galactic terms. It has a warped disk shape full of gas, dust, and bright young stars. The Small Magellanic Cloud, or SMC, sits a bit farther away, about 200,000 light-years, and is more irregular in shape, less structured, more chaotic. Both galaxies are connected, not just by proximity, but by history. They seem to be in a bound orbit with each other, and together they move as a pair around the Milky Way. Their path is a long looping trail that carries them through the edge of our galaxy's gravitational pull. As they move, the gravity from the Milky Way pulls on them. This force doesn't just keep them in orbit, it affects their shapes, their stars, and even their ability to hold on to gas. Over time, gravity stretches and bends them. It draws out long tails of gas and stars, like threads pulled from a piece of cloth. Some of that material is left behind, forming faint bridges and trails between the two clouds, and back toward the Milky Way. One of the most dramatic results of this interaction is the Magellanic Stream. This is a long, narrow trail of gas that stretches behind the two dwarf galaxies as they orbit. It's made up mostly of hydrogen gas stripped from the galaxies by the pull of gravity. The stream stretches across a huge part of the sky, Nearly halfway around the celestial sphere, it's invisible to the naked eye, but radio telescopes can see it clearly. It tells a story of loss, showing how the melanic clouds have been slowly shedding their material as they move through space. The melanic stream may also be feeding the Milky Way. As the gas in the stream drifts toward the galaxy's outer disk, it may eventually fall in and trigger new star formation. This could explain some of the strange patterns seen in the outer regions of the Milky Way, areas where starbirth seems to flare up without a clear reason. If gas from the melanic clouds is falling in, it could act like fuel reigniting parts of the Milky Way's outer arms. Another curious structure connected to these galaxies is the leading arm. This is a stream of gas that appears to shoot ahead of the melanic clouds instead of trailing behind them like the melanic stream. It's less massive and harder to see, but it may be an early sign of how the clouds interact with the Milky Way's own halo. Together, the stream and the leading arm show that this is not a simple orbit. It's a messy, dynamic interaction. The Milky Way isn't a passive host, it's reacting to the presence of these two satellites. It pulls on them, but it also responds as they pass by, sometimes with star formation, sometimes with shifts in the structure of the disk itself. Within the melanic clouds, especially in the LMC, star formation is strong. Massive regions like the Tarantula Nebula are among the most active stellar nurseries in the local universe. These bright, energetic zones are fueled in part by the motion and compression of gas, as the galaxies interact with each other and with the Milky Way. Colliding flows of gas create pressure. That pressure triggers new stars. So even as gravity pulls the galaxies apart, it also sparks creation within them. There's evidence that the LMC has more mass than previously thought. Some estimates now suggest it might be 10 times heavier than earlier models predicted. If true, this changes the balance of the gravitational dance. The LMC wouldn't just be a small companion following the Milky Way, it would be a strong partner, exerting its own pull on the larger galaxy. This could explain movements seen in the Milky Way stars, especially in the outer disk and halo. The gravity from the LMC may be stirring the Milky Way structure, warping it slightly and shifting the positions of stars. Even the Milky Way's dark matter halo might be feeling the effects. As the LMC moves through this invisible structure, it creates a wake like a boat moving through water. This wake could be shifting the center of mass of the Milky Way slightly off-center. It might be subtle, but with precise measurements, it's becoming more noticeable. Scientists are beginning to think that the LMC may even be slowing down as it drags along a part of the Milky Way's dark matter halo with it. Some models suggest that the LMC and SMC may not have been orbiting the Milky Way for very long, possibly just 1 or 2 full passes. That means we may be seeing the start of a process, not the end. The galaxies may be falling in for the first time, captured by gravity after spending billions of years in the outer parts of our local group. If that's true, then the trails and streams we see are only the beginning. Over the next few billion years, the melanic clouds could be pulled closer and closer until they're fully absorbed by the Milky Way. That future is hinted at in the stars being left behind. Some streams of stars seem to extend out from the LMC and SMC already. Early signs of tidal stripping. These stars are moving slowly into the Milky Way's halo, mixing with other ancient stars from past mergers. In the distant future, the clouds themselves may no longer exist as separate galaxies. They'll become part of the Milky Way, their stars scattered across the sky, their identities faded into the larger whole. The Sagittarius Dwarf Galaxy, a slow collision that's still happening. The Sagittarius Dwarf is a faint spheroidal galaxy. It was discovered in the 1990s, not because it glowed brightly, but because astronomers saw a strange concentration of stars in a part of the sky where nothing like that should be. They were dim, old stars, spread out and moving in a particular pattern. That pattern told scientists that this wasn't a part of the Milky Way. It was something separate, something that had been drawn in and was now being pulled apart. The Sagittarius Dwarf Galaxy isn't large. Compared to the Milky Way, it's tiny. Its total mass is just a fraction of what our galaxy holds. Over time, this small galaxy has been dragged into the Milky Way's gravity. Instead of slamming into us all at once, it has been circling, passing through the disk again and again. each time losing more of itself. With every pass, stars are pulled away. The shape of the galaxy gets more stretched. Right now, the Sagittarius dwarf is stretched into a long stream that wraps around the Milky Way like a ribbon. Parts of it are ahead of the main body, others lag behind. These stars are slowly being folded into the outer halo of our galaxy. They become part of us, but their movements still reflect where they came from. By studying them, astronomers can trace the orbit of the Sagittarius dwarf across space and time. What's more surprising is how much this little galaxy has been affecting the Milky Way itself. The disk of our galaxy, which was once thought to be fairly flat and uniform, now appears warped. For a long time, it wasn't clear why the disk had this shape, but models now suggest that the repeated tugging from the Sagittarius dwarf may be the cause. As the dwarf galaxy moves through the Milky Way, its gravity pulls on nearby stars. That pull might not seem strong at first, but over millions of years it adds up. Each pass through the disk creates ripples. These ripples travel through the stars, shifting their positions, changing their orbits. It's not a violent collision like the kind seen in galaxy mergers. It's subtle, slow, and ongoing, and yet it's powerful enough to bend an entire galaxy. When the Sagittarius dwarf passed through the Milky Way's disk, it may have compressed clouds of gas. That compression, even if slight, could push those clouds past a tipping point, leading to the birth of new stars. The timing of some of these bursts seems to line up with what we know about the dwarf's orbit. If this is true, then the collision hasn't just shaped the outer structure of the galaxy, it may have changed its inner life as well. As it passes through the Milky Way, it loses not just stars and gas, but energy too. Its path is slowly shrinking, spiraling inward. Earlier passes took it much farther out. Now it's moving closer to the center. This means the collisions will become more direct, more disruptive, and one day, not far in galactic terms, the Sagittarius dwarf will be gone, fully merged with the Milky Way. We are witnessing the slow end of a galaxy. It happens over billions of years through gentle passes and long stretches of tidal stripping. The stars from this galaxy are now scattered. These stars still carry the fingerprints of where they came from. They move together. They share the same chemical makeup. They're slightly different from stars born in the Milky Way. Astronomers can pick them out one by one and map the flow of the Sagittarius dwarf across the galaxy. There are questions about how many times the Sagittarius dwarf has passed through the Milky Way. Some models say 3 or 4 times, others suggest more. Each pass would have reshaped the orbit, thinned the core, and stretched the galaxy further. With each loop, the dwarf becomes fainter, harder to track, but its influence continues. Like a boat carving a path through water, the dwarf's movement leaves waves that keep moving long after the boat is gone. Our own solar system sits far from the chaos of this slow collision, but in a way, we're part of it too. The Milky Way we live in today is shaped by these ongoing events. Its stars, its gas, even the path of its arms, all bear the marks of encounters like this one. The dark halo and its subhalos, clues to the Milky Way's formation story. The dark matter halo of the Milky Way is enormous. It stretches far beyond the edge of the disk, wrapping the galaxy in a wide invisible sphere. It's not a perfect even sphere. Instead, scientists believe it's lumpy, filled with smaller clumps called subhalos. These subhalos are like miniature halos within the larger one. They're scattered all around, moving through the outer parts of the galaxy. Each one is made of dark matter, and most of them don't contain any stars at all. Even though we can't see these subhalos, scientists have ways to find them. One method involves looking at the paths of stellar streams. These streams stretch out across the sky, and in theory they should be smooth and gently curving, but in reality, many of them are broken, bent, or have strange gaps. Something unseen has disturbed them, something massive enough to tug on stars, but dark enough to avoid detection. That something could be a dark matter subhalo. By studying these disruptions, astronomers can estimate the size, shape, and mass of the subhalos that passed nearby. It's not exact, but it provides some of the best evidence we have that these invisible objects are real. Subhalos also offer clues about the early days of the galaxy. In the early universe, dark matter began to clump together before anything else. These clumps pulled in gas, which cooled and formed the first stars. Over time, some clumps grew large enough to become full galaxies. Others remained small. The Milky Way likely formed from the merger of many of these dark matter clumps. Some merged completely, while others got torn apart or left behind as subhalos. The ones that survived became the small satellites and star clusters we see today, or the invisible subhalos we can only detect through their gravitational pull. In this way, the current structure of the dark matter halo is like a fossil record. It preserves the memory of how the Milky Way was built, piece by piece from smaller parts. However, according to models, there should be thousands of these subhalos around the Milky Way. We've only detected a small fraction. Where are the rest? Are they truly invisible, or is something wrong with our models? This is called the missing satellites problem, one of the biggest questions in galaxy science today. One possible answer is that most subhalos never formed stars. Without stars, they'd be nearly impossible to detect. Another idea is that star formation was stopped early on, maybe by heat from the first generations of stars, or from the radiation left over from the Big Bang. If a subhalo didn't hold on to its gas, it couldn't make new stars and would stay dark forever. There's also a possibility that we're just not looking in the right way. The tools used to find faint galaxies are improving all the time. Some new surveys have already turned up ultra-faint dwarf galaxies that were missed before. These tiny systems are dim and fragile, but they seem to be sitting inside dark matter subhalos. Each one adds a new piece to the puzzle. The shape of the halo itself is still uncertain. Some studies suggest it might be slightly stretched like a football, or even tilted with respect to the rest of the galaxy. These details matter because they affect how stars move, how streams form, and how the galaxy grows over time. The more we know about the halo's shape and substructure, the more we understand the deeper forces shaping the Milky Way.